Grab a sheet. All right, let's get started on this quiz. All right. Number 4 here. Calculate the highest energy visible light for hydrogen when the electron transition from energy level 6 to energy level 2. So here's our equation. So we've got 1 over the wavelength is equal to R, 1.097 times 10 to the 7th meters to the minus 1. This is 1 over n final squared, which is 1 over 2 squared minus 1 over 6 squared. So let's multiply that out. This is 1 over 4 minus 1 over 36. And if we do this, we're going to get a big number here. Because that's 1.097 times 10 to the 7th. We're going to get 240, I don't know, 777.7 meters to the minus 1, I believe. Oops, I'm missing a 7. I got to sneak another one in. I think I need 3 7s here. Okay, so now we just got to, if you put this over 1, you can just take the reciprocal of both sides. The other way to think about this is you can cross multiply and divide. But lambda then is going to be equal to 1 over that number, right? 2, 4, 3, 7, 7, 7, 8, I'll put. That's meters to the minus 1, so that's going to throw it in the numerator. All right, number 5. Energy level 6 to energy level 3. We know that the energy of electron in the level is given by minus RHC over n squared. And then when we looked at this, we factored this out. Okay, so this is, now this is coming down. It's going to start at 6 and it's coming down to 2. So this is going to equal to minus, this is 2.179 times 10 to the minus 18 joules. That's what RHC is. And then we've got 1 over 2 squared minus 1 over 6 squared. Then we did one of these where this is going to be in joules per photon or joules per atom. This actually comes out right away. We don't have to do it in kilojoules per mole. I think it comes out as written. Okay, 20, that's 4, 5, 21. 21. How many valence electrons in 21? Furthest out number we got to right there. That's it. Right? 4s1 is the valence electron. Highest numbered furthest out. 21, 28. A pair of electrons in the same orbital will have how many quantum numbers in common? Well, we can just do that. It's a pair of electrons. Let's say this is a 4s. If this is in a 4s, my quantum number for this one is level 4. 0 for S, 1 for P, 2 for D. So my second quantum number is a 0, right? My third quantum number goes from -0 to +0, so that's a 0. And my last one is 1/2. Yes? Four, 0, 0. What's the only difference? Minus 1/2, right? Those are 2 electrons in the same orbital. How many quantum numbers are the same? Okay. That was 29's on there. I didn't see that. 29, yes. 29. Which set of quantum numbers is allowed? Okay. So this is level 4, -2. We can't have a negative there. Those are 0, 1, 2, or 3s, correct? That -2, right? That's just junk. Well, let's take this one. We've got level 4. So this would be a 4. What does this 2 represent? 0 for 1, 0 for an S, 1 for P, 2 for D. Right? So this would be a 4D. My third number then, my third number can't be a 3, correct? My third number, 4, 2 is fine. My third number goes from -2 to +2. So I can't have a 3 for my third number. That makes that one junk. 4, 3. 4, what's a 3? 4F? 4F? 0? Oh, 1. We can't have a 1 for a spin. That's junk, yes? Can't have 1 for spin. This would be a 4, what? 4S? If that's a 0, we're in a 4S. And my next number could be a 0, yes? And this number is -1/2. That looks good. Because this 2 for sure is garbage, right? That 2 for sure is just junk. Okay, now 36. I thought you guys would have worked on these 2 weeks ago. This was assigned 2 weeks ago. I don't know if I want to spend, I'm not going to spend much time on this. There should have been questions on this like 2 weeks ago. 3 moles here. What mass of nitrogen gas is produced? My mole ratio is 1 to 1. 3 moles. Okay, 37 is a limiting problem. 37 is a limiting problem. We've got 5 grams, 3 grams, ammonium bromide, grams right here. So you need to figure out how many moles of bromine. You need 8/3, and then how much you have. And then get your moles here, and then the grams, right? That is a limiting problem, 37. 38. What do we got for 38? What volume of 2 molarity sodium sulfate? Question mark, liters. 2 mole per liter. Okay, 0.005 liters. 0.135 molarity. Liters times molarity. Here's our moles. This is 1-to-1. So 0.005 times 0.135 is your moles, 1-to-1. Then you've got your moles there. Once you have your moles there, this is in moles per liter. You're going to want to flip this. Take your moles. You're going to want to flip your molarity here. Okay. So this quiz is due when? Friday? Friday, right? Okay. All right, starting Tuesday. If you make it to the rest of the classes in person, the only way to do roll is to have Bailey check your name off. You come to the lectures, I will replace your lowest test score with your final exam score. That will help out 90% of the people. About 85 to 90% of the class will do better on a final exam than they did on one of their tests. Okay, so you have a test score of 70, you get 80 on the final exam, the 70 gets replaced with a 80. It's that simple. And the only way to check in is with Bailey. And don't say somebody else or anything like that, because Bailey's going to turn around and she's going to count everybody in here and make sure however many checks are on the screen matches. So, okay. So I already put a yellow line there, so we'll know. Let's finish this thing off so you can get your all done. So we left off right here. So we did the patterns on the periodic table. So atomic radius increases going down. Ionization energy decreases going down. And we wrote those patterns on your blank periodic table. Now it says arrange the following in order of increasing ionic radius. So this Mg or magnesium, that's magnesium +2. Sodium ion, Na+. oxide ion would be O minus 2. And nitride. And nitride ion would be N minus 3. Well, I actually want to go to the next page and show you this. I think it's more clear on the next page. Well, not the next page, because the next page is the blank table. Page 22. I think these are on 22. Yes. So let's go to page 22. So at the bottom of page 22, I actually had to cheat, and I added this last row here. This is straight out of the textbook. Now, all of these are isoelectronic. So isoelectronic ions have the same number of electrons, but different numbers of protons. One such series of ions is N3 minus, O2 minus, F minus, Na plus, and Mg plus 2. So what is isoelectronic? Same number of electrons. Okay, now look at what happens to the protons. You've got 7 protons, 8 protons, 9, 11, 12. First of all, the atomic radius down here. So this right here is the neutral atom. This is the neutral atom. So this radius here for nitrogen would be 7 protons and 7 electrons. The neutral atom they have to match. For oxygen, it would be 8 protons, 8 electrons. It is a neutral atom. Fluorine would be 9 and 9, right? That's what a neutral atom is by definition. Same number of electrons as protons. Okay, now here you have 7 positive protons. We know these are positive protons. You have negative electrons. The ionic radius, when you add electrons and you make a negative ion, gets bigger. This is almost triple. Almost triple. You have the same number of protons trying to pull in more electrons, correct? Your positive nucleus only has 7 protons. Well, it would make sense that if you have 8 protons and 10 electrons, you can pull it in a little tighter. Not much, 146 to 140. Then if you have 9 protons pulling in 10 electrons, you can pull it in a little bit tighter. You're down to 133. Again, this is about times 3 here. So notice when you go from a neutral atom to a negative ion, it's almost triple the radius. It's almost triple. Now, for sodium, you have 11 protons pulling in 10 electrons. That should be able to pull it in pretty good, right? You have more protons pulling in less electrons. So that pulls it into 98. Notice that this is about half the radius. Not only that, you're getting rid of an entire level. You're getting rid of that S1 electron. This is about half the radius. So what you're looking at for a pattern is the more protons, the tighter you can pull in the same number of electrons. So I'll kind of answers that question then like this. In order of increase in ionic radius, Mg plus 2 is less than Na plus, is less than O minus 2, is less than N minus 3. I think that's how I'll put that. I'm pretty sure that's how I'll put that. Okay, we were on one page here. This last, we just got a little bit here. Electron configurations of ions. Why are we forming ions? Goulet, is that what you're looking up? How do we form ions? Huh? Now, you're not the alone running on your phone in the top up there. You're not the Lone Ranger. We're at the end here, you guys. You cannot cash it in now. You need to step up your game, get on a bigger freaking horse here. Step it up here now at the end. This is not the time to drag your feet on anything. Okay? Get the class, get ahead in your stuff. If you're going to come to lecture and be on your phone, why come? You're just going to be on your phone. You're going to step it up here at the end. We got a lot to do yet. Okay. So, electron configuration of ions. Why do you form ions? To become more stable. What are the most stable compounds? Noble gases, correct? Noble gases. So, fluorine right here has 9, it has 7 valence electrons, correct? 7 valence electrons. What's it want? It wants 1 electron to be like the noble gas, neon. Then it's going to have 8 valence electrons, correct? That's the game. 8, 8, 8, 8, unless you're close to helium, 2. So you come over here. Sodium. It has 11 electrons. It wants to get rid of 1 electron, correct? If it gets rid of 1 electron, this is going to be 3s1, correct? 1s1, 2s1, 3s1. It's going to want to get rid of that electron. Then how many valence electrons will it have? 8, the same as neon. That's the game. 8, 8, 8, 8, 8. So here's the fluorine neutral atom. 1s2, 2s2, 2p5. How many valence electrons? 7. It's going to gain an electron. Here it is. 5 plus this 1, 6. What do you have now? You have fluoride ion, right? You have fluoride ion. This is fluorine. FLU. This is fluoride, right? Negative charge. Fluorine, fluoride. Ion. Okay. Sulfur. The neutral atom ends in 3p4. Again, these are neutral atoms, no charge. What's it need to do? It needs to gain 2 electrons. What is my valence electrons now? Noble gas, correct? This is my noble gas. What noble gas do I have right here? That's neon, correct? 10 electrons, neon. This noble gas right here, argon. That's the name of the game, correct? You are trying to be like a noble gas. You either got to get rid of some electrons or you want to gain some electrons. That's the whole goal. And if you lose or gain electrons, you have ions, correct? You have ions. Sodium atom. What's this thing want to do? Neutral atom. It wants to get rid of that, correct? And if it gets rid of that one electron, sodium ion. Noble gas configuration. And this noble gas, neon, correct? You got germanium, and I actually did the shorthand way now here for germanium. Four S2, 4P2. So in this case, germanium, if it gets rid of these two electrons, we get the +2 charge. Now, germanium could also get rid of, it could also get rid of those two as well. So if I look at germanium on here, if I can zoom in or just hold it up, I guess. 2 or 4, yes? Which one's bold? 4, right? So what it usually does is it gets rid of this one as well. And if it gets rid of this one, we would change this to a 4, and we'd have germanium with a +4 charge. Titanium can be a 2 or a 4. If titanium gets rid of these two, that's the +2 ion. If it gets rid of these two, that's the +4 ion. Okay, iron. Iron we know can be +2 or +3. So if iron gets rid of these two electrons, we get iron with a +2 charge. And then look what it does. So this is my +2. In order to have a +3, it needs to get rid of one more electron, right? If it takes one out of the D, we end up with this configuration, and it stops. This is really stable, all 5 up or all 5 down, right? Half full, half filled is really stable. Okay, so again, the name of the game is just adding or removing electrons to get like the nearest noble gas. Okay, we know that if we have 2 electrons in the same orbital, opposite spins, correct? And remember, this spin aligns with a magnetic field. So 2 electrons, or let's just do it right. I think elements and compounds that have unpaired electrons are attracted to a magnet. Such species are said to be paramagnetic. Substances in which all electrons are paired with 2 electrons of each pair having opposite spin experience a slight repulsion when subject to a magnetic field. They are said to be diamagnetic. So on the next page, we just have this 4s1 electron. This is my 4s1 that's not paired, right? And I guess I should put that in an orbital by itself. Unpaired. So, paramagnetic. Everything here, this is 3D10. Guess, I don't know if I can even do this. I guess I can. D10. Everything's paired. Diamagnetic. And 3D9. I should make this a lot bigger. But we've got one unpaired, right? Okay. Let's go to the very last thing. This isoelectronic. Remember, isoelectronic series. Same number of electrons, right? Same number of electrons. Same electrons. Okay. We've got ions of charges 1, 2, -1, -2. These are going to be metal ions, correct? Our negative charges should be nonmetals. And we have a neutral atom. Give the symbols for 4 species that are isoelectronic with potassium ion. How many electrons does a potassium ion have? +1, so it got rid of 1 electron, correct? 19. Started out with 19 electrons. If it has a +1 charge, it's going to be 18 like argon, correct? So that's my neutral. So my neutral is argon, 0 charge, 18 electrons. $18 electrons with, okay, so that's my neutral one. 18 electrons. Which one of these? Oh, +1 is the potassium. +2. This is my +1 right there. My +2 is going to be, what's my +2 going to be? This calcium here, 20 electrons. If it loses 2 electrons, it's going to take on this +2 charge. How many electrons is it going to have then? 18, right? So my +2 is calcium. My -1. which one is going to gain 1 electron to get to 18? And gaining 1 electron to get to 18 is going to be chlorine, correct? Chloride. And then which one is going to gain 2 electrons? Sulfur, right? Sulfur, 16 to 18 would be a -2. Gaining. All of those have 18 electrons. Okay, I'll question. A monoatomic ion with a charge of -1 has an isoelectronic configuration of 1s2, 2s2, 2p6, 3s2, 3p6. That's with the -1 charge. What's the neutral atom going to end in? What's the neutral atom going to end in? 3p5 for the neutral atom, correct? This is the ion. What ends in 3p5? The neutral atom is 1s2, 2s2, 2p6, 3s2, 3p5. Again, this is the ion. This is the atom. What do we got? 17 electrons. 17 electrons is Cl0, right? Chlorine, 17 electrons. This ion here is the chloride ion. So I'm thinking the ion is, I think it looks for a name here, chloride. What is the chemical symbol of the noble gas? This ion is isoelectronic with the noble gas. 18 electrons, right? The ion has gained 1 electron, argon. And the formula for the ion, Cl -1. All right, that ends this. I don't remember. We left one quiz question, right? All but 33. What is 33? Yeah, 33 we already answered. I think we pretty much answered 33. We talked about the charged ions. Okay, let's put this away. We are done. We are going to the very last 8 and 9. So this is it. So I put this together and we're going to be going paging back and forth quite a bit. It's just how it is. In order to explain it, I'm going to be moving to multiple pages a lot. Okay. This is all about bonds. Ionic bonds, metallic bonds, covalent bonds. This is all about bonds. Now, for a metallic bond, I like to say it this way. If, let's say this faucet right here I don't know, it's disconnected down there, but I want to hook it up to a water hose. I want that water hose go to the same power plant that puts electricity into our lights. That power plant could be the Prairie Island Nuclear Power Plant in Red Wing, Minnesota. Does anybody know where that is? Well, it's a ways. Let's just say that. It's in Red Wing, Minnesota. There's where the nuclear power plant is. Question. We flip on the lights here. What makes these work? Electrons, correct? The flow of electrons. We flick on the light. Did that electron come from Red Wing, Minnesota? Boom, through our lights, just like that? No. They might have pushed those electrons out days ago. And those electrons are making it down the power line, correct? So when I flip the light on, that electron might have started from the power plant, like I said, days ago. It's the same concept of this. If I take a water hose, run that water hose all the way to the power plant. And that water hose is full of water. It's pushing water from the power plant. If I turn this water faucet on, did that water molecule instantly come from that power plant? No. Am I going to get water out? Sure, I'm going to get water out, but that water might have started that plant days ago, correct? So a metallic bond works because it doesn't care which electron is around it. So it kind of works like this. For a metallic bond, if I have copper, would be the best example. So I've got copper, I've got a chunk of copper wire, say. Copper has electrons around it, of course. These are called delocalized electrons because they don't care which copper they're around. So if this is my copper wire, it's no different than my hose. My power plant adds electrons. My power plant is adding electrons. That electron around this copper can go to that copper. This electron can go to that copper. That electron can go to that copper. And that electron can go to that copper. And this electron can power our lights, huh? So for a metallic bond, it's just what's called these delocalized electrons. That's what gives metals luster. But this is a flow of electrons, correct? It would be no different than a flow of water. If you have a higher voltage, you're pushing those electrons with more power. If you have a taller water tower, you're pushing the water to us with more power. So a metallic bond is just these delocalized electrons. That's why we can bend copper. Those electrons kind of reorientate themselves. We can pound copper flat. Those electrons reorientate themselves. Then for an ionic bond, such as NaCl, we say that sodium gives up an electron. What is this electron right here for sodium? That's my 3s1 electron. This is my 7 valence electrons. This is 3s2, 3p5. 7 valence electrons, correct? If chlorine gains 1, this becomes a 6, and I get 8 valence electrons. That's what they want, correct? If sodium gets rid of this one, same number of electrons as the noble gas neon, correct? Chlorine gains 1, 3p6, the same as the noble gas argon. Both of them are happy. For ionic compound, ions have noble gas electron configurations. We really talk about this electron leaving one and going to the other. That's not quite 100% true. If we have covalent bonds, so we use the word for ionic, we use the word electron transfer. For covalent bonding, it's all about sharing of electrons. It's all about sharing of electrons. And what are those electrons we're talking about? Outermost valence electrons. In most chemical compounds, electrons are shared unequally between atoms, with the extent of sharing varying widely from very little sharing, mostly ionic. Excuse me, that should be mostly covalent. No, little sharing. I'm sorry, that's right. Mostly ionic to considerable sharing, mostly covalent. That is correct. Okay. This last unit is all about covalent bonding and Lewis structures. So I'm going to come down to here. We know valence electrons. In molecules or polyatomic ions of only non-metal atoms, the atoms are attached by covalent bonds, by sharing electrons. Non-metals. Carbon dioxide. Just non-metals, right? Carbon dioxide, water. Okay. American chemist Gilbert Newton Lewis introduced a system in which the symbols represent the nucleus and core electrons. That is the non-valence electrons. And the valence electrons are represented by dots. The symbol is the nucleus, protons and neutrons, and the non-valence electrons. So it looks like this, typically. If we write down the symbol of the element, that represents the protons and neutrons in the nucleus and the non-valence electrons. We will then put the valence electrons around the outside, typically in regions just like this. So it says draw the atomic symbol. This represents the atomic nucleus along with the core electrons. If we take calcium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. This is my core electrons. I have two valence electrons, correct? Just these 4s2 is my valence electrons. So this symbol right here includes all these non-valence electrons, the protons and the neutrons. Then if we put these two electrons in, we put electron dot here and an electron dot there, as far apart as possible, either left to right, up, down. It would not matter. Two electrons, you put them as farthest away as you can. So here's how this would look like. So here's my electron dots. This is group 1, has one valence electron. We would just put it in like this. Group 2 would have two valence electrons, one on each side, as far apart as possible. This would be group 3, or I would call this group 13. 3 valence electrons, right? The ones place, try to put them as far apart as possible. Group 14, 4 valence electrons. Group 15, 5 valence electrons. Group 16, and so on, 17 up to 18. Notice right here again, these are noble gases, 8 valence electrons. Now, remember, the valence electrons are the ones place, right? That's our valence electrons. Now, the only way to understand this, we're going to go straight to writing out a Lewis structure. And that is going to go way to page 24. We're going to page 24. Now, I've got some owl examples in here too, because owl gets a little bit finicky at things. So we're going to use page 24 and 25. We're going to draw some Lewis structure. I'm going to show these videos in class when we get to hybridization. Did everybody pick up a single sheet down here? We've got it. I am going to bring you blue sheets. It's got to be blue. So I'm going to bring you blue ones next time. Okay. So we're going to follow this order. And I'm just going to page back to this, but we're just going to dive into one, which is the next page. So we're going to draw the Lewis structure for CH4. So we need to know what our valence electrons are. So I'm on page 25. Page 25. How many valence, my total valence electrons? Well, how many valence electrons does carbon have? How many valence electrons for carbon? How many valence electrons for carbon? How are you going to find out? What group number is it in? 14, so it has 4, yes? How many valence electrons for hydrogen? Group 1, yes? So I have 4 plus 4. I have 8 valence electrons. That's step 1. Step 2 is to put your central atom. Now, typically your central atom is written first. It's going to be the lone atom a lot of times. So we're going to put carbon down. We've got 4 hydrogens to put down, as far away from each other as they can. 4 hydrogens around the carbon, as far away as we can get them. So we're going to go top, right, bottom, left. We're going to make a bond with them by adding electrons. We do not need anything with multiple bonds. We are done. How many valence electrons? 8. How many electrons do I have? 8. Everybody's happy. Why is everybody happy? Because hydrogen has 2 electrons, just like the nearest noble gas, helium, correct? Each hydrogen has 2 electrons, like helium. Carbon has how many electrons? 8, correct? Carbon's happy, it has 8. That's the goal, always 8. What is the goal? 8. To get a stable octet of 8. Stable octet of 8. That's the goal. But helium, or excuse me, hydrogen, has 1 electron. It only needs 2 to be like helium, correct? So now here's this concept of bonding domains and non-bonding domains. Bonding domains are the total bonds on the central atom. So the bonding domains, let's see, am I on the screen? Total bonds on the central atom. It doesn't matter if it's a single, double, or triple bond, it only counts as 1 bonding domain. Non-bonding domains are just non-bonded pairs. And I'm going to show you a video before we get done here. So, for a compound, how many bonding domains? Total bonds on the central atom, carbon. Carbon's my central atom. How many bonds do I have? You have 4 single bonds, correct? 4 single bonds. Is there a pair of electrons not bonded to anything? No. This is a 4-0. Now, I'm going to spoil you this with my blue sheet. We're going to write some things down. I'm going to explain it more later. Bonding domains, non-bonding domains. 4-0. What type of shape? Tetrahedral. What's my angle? 109.5. What is my hybridization? Sp3. Now, we're going to explain that. We're going to write it down for now. Sp3. Now, My electron pair geometry is possible bonds. So my electron pair geometry considers possible bonds. So by that, this is what I mean. This has 4 bonds, correct? Pretty soon you're going to see of a pair of electrons not bonded to anything. So my electron pair geometry for this, it has 4 bonds. If I had a non-bonded pair, it could have 5 bonds. So my electron pair geometry here is 4 bonds. And that 4 bonds is tetrahedral. Now I have molecular geometry, shape, and angle. So my molecular geometry is this 4-0. That shape is tetrahedral as well. And my angle is 109.5 degrees. All right, let's do the next one. We have CCl2F2. Total valence electrons. My total valence electrons for carbon is 4. It's in group 14. Chlorine. Two times. What group is it in? 17. So 7. And my fluorine is 2 times 7 again. Yes. So my total valence electrons is 32. So for my total valence electrons, remember the group number, we can get the valence electrons from the group number. Add electrons for a negatively charged ion, subtract electrons for positive ions. Okay, step 3, draw a bond between the central atom and each surrounding atom. So let's do that. Chlorine is going to be my central atom. I'm going to have Cl, Cl, F, and F. Now I'm hoping you're thinking to yourself, well, why did maybe he could have drew the Cl on top and Cl on the bottom, and then the F and the F across. We could have drew those across from each other. And when I bring my models next time, you realize it won't make any difference. So it doesn't matter. You could have Cl, Cl here, and F. It doesn't matter. Okay, so I got my 4. These are called terminal atoms. I'm going to have to connect them with a pair of electrons. Yes? So let's connect them with a pair of electrons. So we just did step 3. Draw a bond between the central atom and each surrounding atom. Step 4, place lone pairs of electrons about each terminal atom to complete their octets. 4 electron pairs around an atom, 8 electrons. Hydrogen can only have 2. Okay, no problem. This chlorine already has 2 electrons thanks to the way I drew the bond with carbon, yes? So 2, 2, 2, 2, 2. I add 6 more. And if I add 6 more, that chlorine has 8. Sharing the 2 bonded in the middle with carbon. This chlorine do. I just start singing now. Or I go do, I guess. How many electrons did I put down? How many total electrons do I have? How many total electrons do I have? 32, correct? 32. How many am I allowed? 32. I'm done. Everybody's partying it up. Everybody's happy. Why is everybody happy? Everybody has 8 beers. I mean electrons. Everybody does, right? That chlorine has 8, yes? This chlorine has 8. And then, if I can get my fingers right, carbon has 8, yes? Everybody's happy. How many single bonds do I have? 4. How many non-bonds? 0. The rest of this is going to be the same. 4, 0, Sp3. 4 bonds is going to be tetrahedral. And my molecular shape is 4, 0, tetrahedral. And 109.5 degrees. Okay, I want to show you bonding domains, non-bonding domains.
Task is on molecular shapes. The arrangement of pairs of electrons around the central shape, if we have an electron.
This bonding domains on the screen right now, all 3 of those are 2, 0. Remember, it doesn't matter if it's a single, double, or triple bond. It counts as 1. Right? So all of these have 1 on the left, 1 on the right. This is 2 bonding domains, 0 non-bonding domains. The electron arrangement assumes that you have everything bonded 2 bonds. This is linear, and the shape of this is linear both.
Two pairs of electrons around the central atom that's missing, you'll get a bent shape.
All of these bonding domains is 3, 0. On this central atom, the boron, this is 3 single bonds, correct? And all the pairs of electrons are bonded. This is a single bonding domain, even though it's a double bond of 4 electrons. So this is 3 bonding domains. This is 3 bonding domains. Notice the electron arrangement and the molecular shape trigonal planar. 3,
with atoms around this, that results in a trigonal planar shape. Let's look at the next example of a trigonal planar electron arrangement, which is the bent molecular shape. And it just has the same number of electrons, as you can see.
All of
from
these are
the
2-1s, correct?
diagrams. It's just missing
2
atom
bonding domains
trigonal planar geometry.
and
So
1
it's
non-bonding domain.
Molecular shape. This bent shape has 3 pair.
2 bonding domains, 1 non-bonding domain. So now the electron arrangement is trigonal planar because you could have a third bond, yes? So the electron arrangement always assumes everything that could be bonded is bonded. So my electron arrangement is trigonal planar, but my molecular shape is bent. They do not match. So 2-1, 2 bonding domains, 1 non-bonding domain gets me my molecular shape. My electron arrangement, you're assuming we're gonna get 3 bonds.
Pairs of electrons around the central atom. And we have the nitrate ion, the chlorine, nothing from this associated with them. So we have
All of these here are 4 zeros, 4 bonding domains, 0 non-bonding domain. Since everything's bonded, my electron and molecular shapes match. If I have a non-bonded pair, they're not going to match. So these are all 4 zeros. Notice as they rotate in space, this is in 3D, correct?
this ammonium ion happens to have a positive charge, phosphine in the hydrogen.
So we have a non-bonded pair, so the molecular shape and the electron arrangement do not match. This, for molecular shape, is a 3-1, 3 bonding domains, 1 non-bonding domain. What shape is that? Trigonal pyramidal. I'll show you exactly what that looks like when I bring some models next time. My electron arrangement assumes that this is bonded. If you have 4 bonds, it's tetrahedral.
Behaves.
These are all for a molecular shape, 2 bonding domains, 2 non-bonding domains. But the electron arrangement assumes that you could have 4 bonds. So that's still tetrahedral.
Easily guess that this central atom has 5 pairs of electrons around.
And then we'll be talking about these. As these are rotating, you're going to draw these out in OWL.
Central atom.
And we're going to talk about the shapes of these, the angles of these.
Have 4 of those.
Okay, for the quiz, for 8 and 9 take-home quiz. You should be able to do 1 through 3 on this take-home quiz. All right, we'll see you on Tuesday if you're here. Remember, check in with Bailey when you come on Tuesday. The only way is for Bailey to do the attendance starting Tuesday.